All right. So the parabola, your minimum or maximum is going to be your vertex. And that one's really easy to find. Okay. However, when we start to get to like cubics and quartics and trig functions and stuff like that, finding our minimums and maximums are a lot more complicated. So every problem can have, they do not have to have, an absolute maximum and an absolute minimum. Okay? So your absolute maximum will be the highest point on that graph. Your absolute minimum will be the lowest point on that graph over the entire domain or interval that we're looking at. Okay? If we're looking at it as on an interval, so it doesn't go to infinities, you will have an absolute maximum and an absolute minimum. You have to. It could be the endpoints, but you will always have an absolute maximum and an absolute minimum. You also can have local maximums and local minimums. Those are ones that are peaks, but not necessarily the highest peaks. So let's think about a graph. What could you tell me about the peaks? What are some information you know about a peak of the graph? Yeah.
That's where a function begins to increase or decrease.
Okay, so it changes, right? It's going to either go from increasing to decreasing or decreasing to increasing. Yeah, so let's look at, I'm just going to make up a question real quick. All right, so let's look at this graph. So we have this graph. So we talked about how it changes from increasing to decreasing or decreasing to increasing. My slope at those points have to be 0. So that means my derivative would have to be 0. Okay, so now we can start to see how we can use derivatives to start finding our maximums and minimums, right? When you were looking at it in pre-calc, the one thing that was really easy for you to find was the x-intercepts, correct? That was one of those ones you just take the problem, you set it equal to 0. So like in this case, I have 3 x-intercepts. Okay. So we can set a problem equal to 0. You did it multiples of ways. The first way you were taught was just to literally factor the problems out. Okay. What was the first one? Factor them out. You also learned the rational value theorem, where you sat there and looked at the first number and the last number and did all those values. You could use long division to break things up. You could use the quadratic formula. So those are all methods you use to find zeros. Being able to find the peaks and the valleys were a little more complicated. However, now that we have derivatives, we could find the derivative of it, set that equals to 0, and that is going to give me my peaks. That's going to give me my minimums and maximums, because that's going to tell me where the slopes were 0. So if we look at this one, what's the derivative of this? Minus 4 times 1. Okay. Oh, minus 1, not 2. There we go. I was like, wait, it doesn't work. All right, so let's look at this. So I have a minimum right here, right? And if we look at my derivative, that's where my derivative is 0. I have not a maximum there. I have a maximum there. And again, that's where my derivative crosses 0. So those values are known as my critical numbers, which we're going to talk about in a little bit. All right, so let's look at this problem. All right, let's find my derivative, or do we want to find our minimums and maximums for this? This one is on an interval. Okay. So we're going to test. We need to find those 2 points as well. When we're looking for our interval, those 2 points are going to matter. But the next thing we want to find is our derivatives. We can find those critical values. So what's the derivative of this?
Well, x cubed minus 48x squared plus 36x.
Okay. So where does my derivative equal 0? No, not that's not what I meant. That's 0 plugging in. Where's my derivative equals 0? How could I solve this? Now we get back to your algebra skills. What's the first thing we're going to want to do? Yeah, factor out a 12 and a x. The x is actually more important because by factoring out the x, I now have it down to a quadratic, which I can have a lot of methods to be able to do. So let's pull out the 12 and the x. So I have x squared minus 4x plus 3. So we're looking for two numbers that multiply to 3 and add to -4. Yep. Okay. So what are the other 3 points that I can try? So I have 0, 3, and 1. All right. No, 12x equals 0 is 0. So once you get it factored out, you said each part equal to 0 and solve for x. In this case, that's 0. All right. So find me plug those 5 numbers into the original problem. Because so when we find those values are where something happens. We don't necessarily know what happens at those points. We just know something happens at those points. So what's the answer for -1? What's the answer for 4? Was it 32? 0 is? 3 is? Is also 0? Oh, okay. I was gonna say it shouldn't have been 0. And what was 1? 5. Oh, wait. All right. So what is the absolute maximum? What's the highest point on the graph? 37. So that's my absolute maximum. And that was one of the endpoints. What's my absolute minimum? Oh, sorry. Actually, probably max and min both have the same letters. That's not going to help me. What's the absolute minimum?
-27.
-27.
Wait, would it be -27 or 3?
The absolute minimum is -27. It's the point. So you'd write it as a point, the x and the y. The absolute minimum occurs at x equals 3, and the value is -27.
Thank you.
No problem. All right. Do I have any local minimums or local maximums? Okay. So the question is how do we figure that part out? Absolute minimum max is easy, right? It's the highest point and the lowest point. The locals are a little more complicated. So for right now, the only way for you to determine if local mins and maxes, you have to graph it. Just throw it in a calculator, graph it, and see what the values are. So in this case, next class, you'll actually be able to figure that out. Not going to go that long. So 0, 0 is a min, and 1, 5 is a max. So that's a local min, and that's a local max. This value is none. Your endpoints cannot be local. Your endpoints has to either be an absolute or nothing. Okay, so since 4 is an endpoint, that isn't a max or a min. Okay. How do you think we'd figure out a local min or max? We know that the derivative is 0 at that point, right? Okay. What a local min, what's about the graph tells you what's happening at a local minimum? It's going to be going which direction in and which direction out. It's going down to it, right? And then up. Okay. So if the graph's going down, what should we be, what can we say about that? The derivative is going to be negative. It's going down, my slope is negative, right? So that means my derivative is negative. If it's going up, my derivative is positive. So if we look at those points and we figure out if the derivative is positive and negative on which sides, we can then determine if they're local mins or maxes. We'll do that next class. We're not doing that right now. We actually start looking at sketching the graph. That's one of the pieces of information we're going to find out. All right. So does this make sense? Yeah.
I'm just trying to visualize the graph because I think what's messing me up is the fact that the F's are in order. Because I think I understand.
Hold on, I fixed the graph. Here's the graph. That's what the graph looks like. So it's going there. It's going down. So this slope would be negative. It's 0 there. It's positive after that point. It's 0 there. It's negative after that point. it's 0 there, then it's positive. Okay. All right. These two things I've just already taught you. If it has a local minimum max at C, then the derivative exists. Then the derivative has to be 0. Your critical numbers, the ones we've looked at so far, is when my derivative is 0. We also can have a critical number where the derivative does not exist. Okay? That's important to keep that in mind as well. All right. Really simple. F of x equals x to the third. What's its derivative? So what's the critical numbers? Yep. And that's it, right? Okay. So if I plug 0 into the original problem, my point is 0, 0. Is that a minimum or a maximum?
Origin?
Yeah. What's a cubic graph look like? So there's my cubic. So is 0, 0 minimum or maximum? It's neither. For it to be a minimum or maximum, it has to change direction, right? It does. This one doesn't change direction. So just because it's a critical number does not mean it's an automatic minimum or a maximum. You do still have to look at that. So this is a situation where it's just not. All right. Let's do the word object. Okay. Let's do rocket science. No. This is talking about the shuttle going up. So this is rocket science. It's actually, out of all the things, so how many of you have actually ever, I know, okay, let me actually rephrase this. Has anybody actually seen a live rocket launch?
Yeah.
Where have you seen it?
Florida.
Very cool.
Years ago, I saw one.
Okay. So have you seen one online? Okay. Have you seen one blow up online?
Yeah.
All right. So where do you think the most likely chance for a thing to blow up would be? Okay. So when it's first going off, which we've had, and when it has those maximum loads, because that's where the most pressure is going to be on the seals and all those other things that could possibly go wrong. So understanding where those loads would happen is important. Okay. And when we're looking at this problem, that's the velocity equation. So velocity is great, tells us the speed. But does velocity tell you the forces that are acting on? That's going to be your what? That's going to be acceleration, because that's how fast things are changing, right? So we've got our velocity. How do I find my acceleration? It's the derivative. So find me my derivative of this. All right, so what's my derivative? You'll notice these derivative problems are a lot easier than some of the ones you just did. All right, so what's my derivative?
0.003906 t squared minus 0.1805 plus 23.61.
Okay. Awesome. Now I need to find my what? I need to find my critical numbers. Okay, so once we find our critical numbers, then we can start looking at the mins and maxes. So I need to find out where this is 0. Okay, so find out where that's 0.
Professor, is there an easy way to factor this?
Not factor. I don't think
What?
I don't think there's an easy way.
Like to put in those parentheses? Times parentheses or?
I think quadratic formula. Some of the others, some others like quadratic formula.
Can you split the square root of this?
Huh? No.
Do we plug the 126 in now or that's later?
No, that's later.
Which one are we trying to figure out? The t squared or the t cubed?
So come on, 50 squared.
Okay, I'll make your life one step. I'll make your life a little easier. I misread the problem a little bit. They want the absolute minimum maximum values of the acceleration. So we want the critical numbers of the acceleration, which means we need to go one step further. We need to find the derivative of this.
That was supposed to make our life easier.
It is. What's the derivative of this?
Oh, yeah, that's just a
Oh.
simple.
Huh? Yes. So we're looking for our minimums and maximums acceleration. So we're not looking for the minimums and maximums of velocity, which is what you would do with this one. So what's the derivative of this, of acceleration? Which would be jerk, yeah. But so I got 0. T. Oh, there's 2 zeros. That's okay. Minus 0.18058. Okay. When that equals 0. Now it's just a simple linear equation, which is a lot easier than doing your quadratic formula, which is what you should have done for the last one. Was it 126? What was 126? Yeah, 126. All right, so what's the value for when that equals 0? So 115. So 1 we'll do. All right, so now plug those 3 values into my acceleration. Acceleration. Because we're looking for our minimums and maximums of acceleration at this point. So remember, one of the things that I'd shown you before is if you plug into the Desmos Scientific Calculator, you plug in 0, you get 23.61. What was it? 2312. Plug in that, you get your answer there. So it's 21.52. And then if you change that to 126, 62.87. So you can use the Desmos Scientific Calculator to plug those numbers in quickly. Makes life a lot easier. Yes. It was the beginning and the end. So the original problem had said that the solid rocket boosters were jettisoned at 126 seconds. So those are the endpoints. It's 0 seconds liftoff and then 126. So my minimum acceleration is 21.52 feet per second. And my max, or feet per second squared. And my maximum acceleration is 62.87 feet per second squared. How many people are in physics? Why does my minimum acceleration not occur on liftoff? You would assume that'd be where like it should increase from to that point, but it doesn't. As the rockets go up, they lose a little bit of their power, but also gravity starts to pull down more. So that's why it actually slows for a little bit before it actually starts to accelerate after that point. But it's minor. It's only like less or 2 feet per second squared. It's a very small change, but that's why it's not at 0. Yeah, the mass changes too. But the mass is going to change throughout the entire thing because the actual it's burning off the fuel. So that's why, like the most expensive part of the rockets is the fuel to actually get it to lift off. There's more weight in that than actually the weight of the actual rockets. So if we can somehow do that from space, we would have that problem. It'd be a lot easier. We just need to figure out how to get to space easier. Once we do that, it's golden. So, but that's also why SpaceX works on like retrieving all the rockets and stuff like that, because that lowers their costs. So, and it makes it easier for them to keep blowing up their starships as we're going. But they almost made orbit the last one. So then I think the next one will actually make orbit. So yeah, but it didn't actually orbit. It actually went up in the right. Yeah, they didn't have. It wasn't. But apparently, and you never know with SpaceX because every failure is like that was planned. They said they never planned to make orbit with this one, but from like what was it last November they did their first one. It was like late last year that they did their first one to now. They've actually they've iterated pretty good quickly to be able to go from something that literally blew up on the pad to basically in orbit. So yeah. And there's nobody on it. It's just materials. There's nobody on these. No, there's nobody on these. You know, they don't even have dummies on these. These are literally just autonomous rockets. It's all autonomous. It's all computerized. That's what the ones that go to the International Space Stations. There's a commander and a pilot and stuff there. They don't do anything. It's literally all computerized up to go. Yeah, there's people in the space station. Yes. They've stepped there. Some of them have been up there for almost a year. But they just keep orbiting. Every 90 minutes they go around the Earth. All right. Next. So there's a couple other theorems we're going to look at today. Actually, you know what? Before we go into this, I want to do one more of those problems. So I want to do one. Hold on a second. Before I go into Rolle's theorem. Number 40. All right, before I go into this one, I'm going to do one more problem.
Professor,
Yes.
I'm still really fuzzy on what you plugged into here in the 23.61.
Oh, we plugged in the initial points.
So which equation?
The acceleration equation. No, the acceleration. Because these are, notice the A's. The A's were important. So the original problem said that liftoff was at t = 0, and the rocket boosters were dumped at 126 seconds. They gave us our velocity. We found our acceleration. They want to know the minimum and maximum of our acceleration. So we plugged 0, which is the original liftoff, into the acceleration equation that we found, not the velocity. So
Where's the 23.1?
that was my critical value. That was the value we found from when I solved the jerk equation, basically, for 0. That's what I want. There we go. Okay. All right. Find me my critical numbers for this. We're just finding my critical numbers.
Professor, do we need to find the derivative of that?
Yes, you do need to find the derivative of this. So yes, this derivative is a little more complicated than the other ones, but honestly not as complicated as some of the ones you just had in your test. Till we get to chapter 5, yeah. But chapter 5 is the opposite. It's integration.
The next test could be
Chapter 4 only. Nope, just chapter 4.
Wait,
The only chapter 5, you'll see a few questions on the final, but you won't see any of those in the actual tests.
wait, so Professor, the chapter 4 test is just going to be what
Chapter-
we're learning now?
And what we're going to be learning for the next few weeks. While you're doing this one, I'll find the date for you because I can't remember the date off the top of my head. It's after the eclipse. I know that. The next test is on April 17th. Yep. It could be May 8th or May 13th. They haven't sent out the final schedule yet. So we'll be reviewing for the final on May 6th. All right, so this is 4 minus x squared to the 1/3 power. So I have a chain rule. So what's the derivative of the inside? 2x. And then I bring down the 1/3, 4 minus x squared, and subtract 1. And then I get a 2/3. Oh, you're right. Yeah, it would be negative 6. Good catch. Okay, so there's my final derivative. There was quite a few mistakes on the test going from there to there too. Do remember how to subtract fractions. Or use a calculator to subtract your fractions. One of the two. All right, so what are my critical values? So to make this equal to 0, I'm just looking at the top, right? So negative 2x equals 0, so x equals 0. So that's one of them. Are there any other critical values? So when we were originally looking at this, I'll go back, don't worry. That's what we focused on so far, but that also exists. So where the function does not exist as well is needed. So in this problem, so far, this is the first problem that we've done that's had a division in it. So it's the first problem we've had that has things that would not exist because all the rest are just polynomials. So where would this problem not exist? So it's where this bottom equals 0, right? Which in essence is only where the 4 minus x squared equals 0.
What if it with 3/2 is a negative under radical?
It's a cubed root, so the negative doesn't matter. So negative x equals -4. So x squared equals 4. So this equals x equals plus or minus 2. So I have 3 critical numbers in this situation. Okay. The only other thing you have to look at when you get your critical numbers is, are those values part of the domain? So can those values work in the original problem? Since this is a cubed root, I can't have negative values. So, and if I plug these in, I'm still going to get 0, so it's fine. So all 3 of those values would work in my initial problem. So all those would be critical values that I could have. Does that make sense? Okay. So those are the things you have to check after you get your critical values. All right, let's go on to the next stuff. All right. Rolle's theorem and the mean value theorem. So Rolle's theorem was discovered first. And then the mean value theorem is basically a generalization of it. So the crazy part is when I show you this, you're like, yeah, that just totally makes sense. Why did somebody actually have to discover this? Because that's the way the math works. So what Rolle's theorem states is, as long as the function's continuous and differentiable. So basically it means there's no holes and stuff like that. If you plug in a value or 2 values, the endpoints, and they give you the exact same answer, at somewhere in between those 2 values, my derivative has to be 0. So at some point between those 2 values, I need to have a horizontal tangent. Okay? So if you think about it, basically they're saying that if these 2 values are the same, and the function goes continuously between those 2, at some point, it has to turn. Okay? Now, if you think about that, it totally makes sense. It's like, well, yes, it has to do that. There's no way otherwise would you get back to the same exact point you started with without turning around. That's what Rolle's theorem states. No, differential means that it doesn't have doesn't have like the kinks, the points, or that it can, you actually can find a slope value for every point in that value. So every point in between it has a slope. So between here and here, I have two of them. That's fine. Rolle's theorem doesn't state that it can only have one. It just states there has to be one. Okay? And this one goes down. Make sense? Awesome. This is what happens in the 1700. Let's see. So when did Rolls come up with this? 1691. He did that without computers. He did that without electricity. 1691 was a long time ago. No, he was a mathematician at that point. There was mathematicians and stuff like that. This was past like Copernicus and stuff like that, when the Catholic Church basically said, no, we're right and everybody else is wrong. Well, I can't say that we're past that point, but past the point that a lot of people care. We'll go with that direction. So at this point, there was actually mathematicians, theoretic, and people working and coming up with stuff. But if you think about it, everything goes back to war, because in essence, governments paid these people, or like universities and stuff like that. So it's like, if you think about it, if I'm throwing a boulder, or a trebuchet, or a rocket, or an arrow, or at this point they had gunpowder, like things like that. It's like when you were firing it, if I'm here and I need it to go in there, at some point, even a bullet curves. Okay, so being able to aim over long distances, you needed to be able to figure those things out. So by them working with the mathematicians to figure these things out, they were able to do the calculations to be able to find that out precisely. So they were able to become more accurate with their firing. So it's like, as horrible as war pays for a lot of things, like the reason we haven't gone back to the moon is because the Soviets stopped. Like there was no reason for us to compete anymore. So we didn't go back. So it's like, and yep. All right. So I said the mean value theorem is basically a generalization of that. So Rolle's theorem was very specific. F of A had to equal F of B. So those two values had to come back to the exact same value. The mean value theorem doesn't need that to be the case. Okay? It just states that between any 2 points, let me actually get a nice little picture, because pictures are always a good thing. So it says that between the 2 points, actually, it's smaller. The slopes are going to be the same. So if we look at A and B, the difference between Rolle's and mean value theorem, they do not have to be the same point. What the mean value theorem states is that there is a point somewhere between these two where the slope is exactly the same. Okay. While the vast majority of times we're going to be wanting the horizontal slope, that's not necessarily always going to be the case. And the mean value theorem allows us to find any situation when that's the case. So, and it's the same concept. It's like, if I know between here and here, the slope is 1/2, at some point over this curve, the slope's also got to be 1/2. Slope.
Y1 minus Y2.
Yeah, that's the slope equation. Yeah. That's where the slope equation came from. Right there. There's your slope equation.
Really? So you see your math slope?
In essence, there's your slope equation. Now, when we're looking at the slope equation in terms of a linear equation, it's very simple. So, but the slope equation works for any situation. And that's where your derivatives and stuff come into play. So the mean value theorem was discovered, I can't really say invented, discovered by Lagrange. Yeah. Lagrange. And he was a professor in Turing at the age of 19. Yep. 1730s to the early 1800s. He was born in 1736. So he was a professor in 1754 or 55.
Question, Professor.
Yeah.
Are any of these history questions going to be on our test?
Every one of them. That's all I'm going to put on the chapter 4 test is dates and names. No. No. I'm a math teacher. I hate that stuff. He lived to a ripe old age of he died in 1813. So he actually lived quite a while. Like 77 years. So, you know, he lived quite a bit. All right. Let's look at a few problems. Oh, actually, this was the other problem I got in trouble for throwing in my calc book. You'll see why. So the question was on a toll road. You go through a toll booth. Well, now they're all electronic. You go through a toll booth at a specific time, and they know exactly the time you go through that toll booth and exactly the speed you go through that toll booth. Not the speed. They know the exact time and location of that speed that you go through. There's another speed booth 20 miles down the road. They know the exact time and location of that speed booth that you go through. You go through both speed booths at exactly 65 miles an hour. They send you a ticket for going 70 miles an hour. How did they do?
Because when you were going, you went 65 through both.
Right. So they used the mean value theorem. Even though you were going 65 between both, the time it took you to get through it, the slope, basically the slope, the time that it took you to get through it, they knew that at some point during that stretch, you had to be speeding because the slope was higher than it was. Yes. Well, Can it happen? Possibly. I know of one situation where it did happen, but it happened before the electronic ones. It was when you actually had to go through a booth, and I was doing about 120 between the two toll booths. So, Mass Pike was fun. Yeah.
Wait, Professor, how do you get in trouble though? Is that how? You're going 120?
So I made it. So I got on. So on the Mass Pike, I got on in the toll booth that used to be on 84. So when 84 went to I-90, and I got off on the toll booth that went between or was on going to 290, going to Worcester because I was going back up. I was going up to college. So I made that distance, and I can't honestly even tell you how fast, like how long it took me, but I made that distance because it's time stamped on the ticket when you handed it back in. So, and it literally set off a thing because it was like, there's no way you could do that. So it's like, there's no way you should have been able to do this. And the cop pulled me over right after I left the toll booth. So, yeah. Yeah. I was driving a Dodge Omni. An ancient. Go ahead, look up what a Dodge Omni looks like. It's like a little Ford Escort. I don't even make them anymore. And I had this thing floored. Yep.
Let's go. It's funny. I've done 100 and I was scared for my life.
Yeah, like a little gremlin. Yeah.
I hit 100 in my little Ford Ranger before I crashed.
So yeah, so it's like, I had to get back in a specific time, and that's what happened. So can it happen? Yes. That defeats the purpose of I needed to get somewhere. But and I got in trouble for putting this, like, that question basically in my count book because they're like, you're condoning speeding. I'm like, no, it's a perfect example of the mean value theorem. Literally a math problem. But that it literally is. It's like, because they could figure out using that slope. They knew at some point. They didn't know where it happened or when it happened. They just know at some point you had to have exceeded the actual speed limit that it was. No.
They really said you were condoning speeding.
Yeah.
It's like when they make car crash questions in the exam, and I'm saying you're condoning car crash.
So it's fine. It's no big deal. I took the question out. I made it. No, actually, we didn't remove the question. What we did was we lowered the speed so that it wasn't as extreme. So, yeah, I think we lowered it down to so it was like they were in a 65 mile an hour road, and they were going into 70, like that first example I came up with. So, which no cop's ever going to give you a ticket for going 5 miles an hour over the speed limit, but it still fit the entire concept of the mean value theorem. It was like, it's the one example I could come up with, like, this is an actual legitimate real life example of where people use the mean value theorem. So there you go. All right. Let's what do I want to do? What do I want to make you guys do right now? Let's do this one. All right, doing my thing. There we go. All right. Let's get theoretical instead of an actual problem now. Just because it's easier sometimes to work that way. All right, so we've got this problem. And we want to find Using the mean value theorem, find the value of C that satisfies the mean value theorem. Oh, that's a 3. I don't know how. There we go. So, if we go back to what the mean value theorem stated, let me get the actual equation. Why is that calling me? Hold on. Yes. Morning. Good. There we go. All right. So if we're going to use the mean value theorem, we want to find a value of C that makes this true. So the first thing we have to do is we need to find f of B and f of A. That's A and that's B. So how do I find f of A and f of B? Plug them into the problem. So we need to find our original slope for this equation between those 2 points. So f of negative 2 is
Yeah, squared minus.
so f of C, f prime of C equals what? That makes sense? That's not my answer. I need to find C. So what's the next step I got to do? Find my derivative. So find my derivative of f of x. So it's f prime of x.
3x squared minus 3.
3x squared minus 3. So if we plug in, we want to find when f prime of C equals 1. So that's when 3c squared minus 3. So 4 equals 3c squared, right? 4 thirds equals c squared. So 2 over the square root of 3 equals c, plus or minus. And depending on how much of a pain your teacher is, that's what's rationalized. So I have two values of C that will give me my slope of 1. I brought the 3 over. No, I'm not. So I'm not plugging. C isn't 1. The answer is 1. Yes. And then you're solving for C. Because you're plugging in C basically and solving. So that tells me, hold on, let me graph it. It'll make a lot more sense. What was the original problem? X to the third minus 3x plus 2.
Bless you.
Now, equals 2. So all right. So it says I need to find the slope. That's okay. Slope's 1. That's right. 1. Plus 2. Right about there. That's fine. Close enough. So we're looking at the 2 points there, right? So what we found was that between those 2 points, there is the 2 points at x equals 2 square root of 3 over 3 and x equals 2 or negative 2 square root of 3 over 3. So at those 2 points, the slope is also 1. That's what the mean value theorem is telling me. Okay. So at those 2 points, the slope is also the same as that slope. So if I wanted to plug in and find my exact B value, I can find my exact B value to find the tangent line at that point.
Does Desmond do that for you?
No.
No.
Nope. Not this one. So I can make this variable and actually do this. So it's approximately there. So you can actually do that. And it's approximately there. So you still need the equation. Yeah. And all this is doing is approximating. It's not finding the exact value, but it makes a nice little things like, so you could say, okay, that slope at that point right there, I have the exact same slope. Stop. 1. At that point, that's the concept of the mean value theorem. It's one of those theorems that it makes sense. It just in like this is the main thing that changes between math and science. Like in a science class or a scientist go, okay, I've got enough evidence that this makes sense. We're going to go with it. However, 50, 100 years later, I got more evidence that didn't quite work. This is a better approximation of it. Where in math, when we come up with a theorem like this, that theorem will always work. You can never prove that theorem wrong. So it allows us to do other things. Now that we know this, we have the statement is true, we know we can find a slope that's similar to any 2 points. It helps us with that information. So, okay. All right. I think we're good for the day.
Professor,
Yes.
my schedule says the class runs till 11:15.
Yeah. It
So
does.
do we just get out early, like half an hour every week?
No, it's when I'm done with what I need to cover.
You're efficient.
So
Wow.
the more questions you guys ask, the longer it takes sometimes. But I cover more. Yes. Do I have to? No.
We'll take care of that later.
Yes.
I had a question on one of the ones we did. Sure. When we were looking at the critical values and
Hold on one second. Let me just stop this.
Thank you, Professor.
You're welcome.